Okay. Good morning, everyone, and welcome to our NLP Spotlight session. I'm Nguyen, and I'll be your host and facilitator for today. We will be spending time learning about this fascinating paper on the application of NLP for off-topic spoken response detection, which was featured on the 2020 ACL anthology. This paper is authored by no other than our guest for today, Vatsal Raina. Vatsal is a PhD candidate at the University of Cambridge, and he's working on some really fascinating deep learning applications. It's good to have you here, Vatsal.
Thank you, Zach. I'm delighted to be invited to speak at today's NLP Spotlight session, and I really do hope you enjoy hearing about my paper today and do take something away from it. Just to give a tiny bit of background about myself, I have just completed my 4-year intercalated master's at Cambridge in information engineering, and as Zach mentioned, I will be starting my PhD here, where I will be specifically looking at deep learning applications in the realm of speech and NLP.
Okay. So, specifically, the paper we are talking about today is an attempt at classifying the relevancy of a given response to unseen prompts. That sounds very impressive. Maybe you can tell us more about the motivation for your idea?
Yes, so I guess the real motivation for why we are looking at classifying the relevancy of a given spoken response, in particular to an unseen prompt, is due to the increasing pressure on a lot of testing bodies to fairly assess the language abilities of a diverse range of students. It is also clear that there is a rapid rise in spoken language assessment, as both academic institutes and businesses rely on such tests to ensure students and prospective employees exceed some baseline threshold in their English speaking abilities in order so they can thrive in their new environment. So, the only practical way that these testing bodies can maintain capacity to test a large number of candidates on their speaking abilities whilst remaining fair in the assessment is by automating the assessment process. So, off topic detection is just one of these elements that is important to concentrate on, just to check that the candidate really understands the question that they are being posed in an exam. Now, it is clearly more desirable for any off-topic system to be able to handle prompts that are unseen to it, because these testing bodies are likely to roll out new questions that have never been seen before. And it is still vital that any off-topic system in deployment is able to handle these new unseen prompts, which is why in this paper we really focus on boosting performance on prompts that are unseen during training time. I'll explain a little more during the course of the presentation too.
Sure. As an immigrant to Canada and someone who's have to deal with English testing on multiple occasions, I certainly can see the huge benefit of you know this sort of automated system in the market, both for the learning market and the testing market. So, given the recent development in automation and machine learning, how do you imagine this sector will evolve?
So I think it is highly likely that the spoken language assessment sector will evolve quite rapidly in the direction of automation in the next few years. Well, actually, I think we have already begun to see some of this in the industry. For example, some of you may have heard of ETS's speech rater and Pearson's Azella. Of course, such systems still have a long way to go in order to be fully comprehensive of all the elements being assessed in a spoken response by a candidate. Particularly, these kind of systems tend to neglect the relevance between a candidate's response and the prompt, which could potentially mean that by repeating a pre-prepared response that is irrelevant to the question, a candidate could trick the system to achieve a high grade by having impeccable grammar, fluency, and other factors that these systems tend to traditionally focus on. Hence, this is why we put a lot of emphasis on off-topic detection in the paper.
Well, it seems that without further ado, let's get to the presentation. I'm really looking forward to it. So the stage to you, Vatsal.
Okay, let's begin. So, hello everyone. Today, Vatsal, that's me. I'm the first author of the paper, you can see here. I will be talking about a pair of complementary systems for off-topic spoken response detection. But the first question we should really ask, why is off-topic detection important in speech and NLP tasks? Many of you will be familiar with educational bodies such as IELTS, TOEFL, and Pearson. For the rest of you, these bodies offer standardized assessments that are used by academic institutes and businesses to ensure candidates exceed a baseline standard for English proficiency. A key aspect of these assessments involves free speaking tasks where the candidate is required to speak spontaneously in response to a prompted question. In recent years, there has been a shift towards automatic assessment of the candidate's responses. However, these systems tend to emphasize criteria such as fluency, pronunciation, and language choice over topic relevance. This can lead to candidates cheating the system by repeating pre-prepared, rote-learned responses that are off-topic with respect to the prompt. Hence, it is critical that topic-relevant systems are developed to flag off-topic responses. A holistic view of a topic-relevant system is shown on your screen. The response here is spoken, so an automatic speech recognition ASR system is required to transcribe the response to text. So the prompt and the response are fed in parallel to a deep topic model that reports a relevance score between 0 and 1. Here we can see it's denoted by the letter Y. 1 indicates perfectly on topic, while 0 indicates the response is off topic with respect to the prompt. Hence, the Y can, in a sense, represent the degree of relevance between a given prompt and response pair. The work in this paper explores the benefits of two very different deep topic models, which I will begin to describe now. The first model investigated is the hierarchical attention-based topic model, which I will refer to as the abbreviated form HATM. This model is motivated by Malinin in his 2017 paper in ASRU, where Malinin proposes an extension to his attention topic model by introducing an additional attention mechanism attending over a hierarchy of scene prompts. The idea is that any unseen prompt is able to lock on to the vector representation of a combination of the scene prompts by acting as the key for this prompt attention mechanism. A radically different approach was proposed by Wang at Interspeech in 2019, based on representing a prompt response pair in the form of a grid that then permits the use of very deep CNNs to determine the relevance. Here, the model will be referred to as the similarity grid model, i.e. SGM, with an M prepended for the multiple channel version. I'll get onto what this quite means in the next slide. Both these models have shown good performance for prompts seen in training. But it is more valuable in deployment to use the same systems on responses to new prompts that are unseen in training, as it avoids the need to retrain the system. In previous work, the best performing HATM suffers significant degradation, while the SGM has not been assessed on responses from unseen prompts and has no code available. So, we primarily focus on improving the performance on responses to unseen prompts. Okay, let's look at the models themselves now. Let's start with the HATM. We can see the HATM here, where the prompt words are denoted with #X and the response words with #Z. HP represents an encoding of the prompt words, which acts as the key for the response attention mechanism to yield a fixed length vector H. This is used to predict the probability of the response being relevant to the prompt, i.e. the letter Y. Note, HP is generated using the prompt attention mechanism, which attends over the prompts seen in training using the test prompt as its key. All the prompt and response encoders use bidirectional LSTMs, and both the prompt and response attention mechanisms are additive. Also, the classifier that produces the relevance score uses ReLU activation functions. Let's look at the prompt attention mechanism in a little more detail. So, as I mentioned, this orange section represents the prompt attention mechanism. And one of the modifications we incorporated into the HATM was a form of regularization. The attention weight associated with each prompt embedding was randomly assigned to a weight of 0 during training. Hence, this is coined prompt dropout. As you can see, an attention weight is either assigned a weight of 0 or the correct value that it should have been assigned from training, which is simply a softmax function. We found that this form of regularization discourages overfitting to the training data and encourages greater generalization to the unseen prompts. If you didn't quite catch what I meant by this form of regularization, do ask me at the end of the presentation. So the other model we investigated was the SGM. As an initial pre-processing step, we found it beneficial to remove all the stop words and only retain the content words in the prompts and the responses. So stop words might be like the words the, and, it, the type of words which don't actually add much value in terms of the contextual meaning of a prompt or response. However, we found that using only content words by removing the stop words in the HATM degraded performance. So this removal of content words was only applied to this kind of model, the similarity grid model. So returning to the similarity grid, each content word has a word embedding generated, which are then used to construct a grid. We can see an example of a similarity grid in this diagram. Essentially, for each cell position, each position holds an inverse similarity metric between the corresponding prompt word and response word. In order to handle the variable length of prompt and response words, every grid is resized to 180 by 180 pixels. Then, the Inception Network transforms the grid, which we can think of as an image, to a relevance score. In particular, the word embeddings are context independent, and the embeddings for both the prompt and response words are tied. The inverse similarity metric stored in a cell is simply the cosine distance between the corresponding pair of word embeddings. The resizing is achieved by a bilinear transform, and the Inception network selected here, this one here, is just the ResNet 152. So far, we have only discussed a similarity grid with one channel. We can easily extend to multiple channels with different forms of embeddings or distance functions used to compute the values in a given channel. Here, we got best results with 3 channels where different word embeddings are used for each of these channels. The simultaneous training over the multiple channels allows the results from each channel to be complementary in nature, which is why we found the multi-channel SGM to be better performing than the SGM on its own. Okay, let's talk a little bit about data augmentation. Data augmentation is general and can be applied to both forms of the model, as well as to the prompts or responses. However, the focus was on the prompt side, as there are a large number of responses available and only a limited number of unique prompts. We found the augmentation strategies were beneficial for the HATM and not for the MSGM, possibly due to the reduced flexibility by relying on word embedding distances. Both structured and unstructured techniques for augmentation were investigated in order to increase the number of unique prompts available. The structured techniques consisted of 4 simple ways for augmentation of a given prompt: synonym replacement, random insertion, random swap, and random deletion. Back translation was used as an unstructured technique. The original prompt, we can see here the prompt is describe your role at your workplace, was translated to a foreign language. In this example, I've chosen Arabic. It could be any foreign language, and then translated back to English to generate a paraphrased prompt. This new prompt was then matched with the original prompt response to generate a new prompt response pair for training, i.e. we somehow managed to generate a new data point in our training data set. And of course, we can repeat this for many prompts to expand our data size by whatever size that we desire. All the data used was sourced from Cambridge Assessment English, Linguaskill Business, and Linguaskill General English exams. In particular, responses were collected from the prompts in the long free-speaking parts of the test. A typical prompt might be something like, talk about a hobby. I won't reveal the exact prompts because it's part of a real exam, and I don't think I have the approval to do so. We can see from the table that we had 1 training data set and 2 evaluation data sets, which we've called seen and unseen. For example, to understand the table a little better, the training dataset consisted of 379 unique prompts and 257,000 responses, meaning there are on average about 679 responses for each prompt. We can also see that the typical prompt length across all the datasets is between 51 and 55 words, while the length of the responses is between 42 and 48 words. We also report the average number of content words in the prompts and the responses because the MSGM performed better using only content words. All the data is taken from tests assessed by human examiners, which allows us to assume that all responses in the data are on topic. The diagram here depicts the method by which synthetic off-topic data is consequently generated for training and evaluation. During training, a dynamic sampling mechanism matches responses from one prompt with a different prompt. Balance is also maintained such that the distribution of topics in the on-topic examples is similar to the off-topic examples. The shuffling method allows us to distinguish between the seen and unseen evaluation datasets. Dataset seen is formed from prompts that have been seen during training and negative responses that correspond to a different set of prompts also seen during training. In contrast, the unseen evaluation dataset consists of prompts that are unseen during training and negative responses that are also unseen during training. Note, it is quite justified to generate negative examples by permuting on-topic examples, because candidates intending to cheat can expect to repeat a pre-prepared response which would have come from some different prompt. In evaluating our models, we selected f0.5 as an appropriate metric in place of f1, as there is greater interest in achieving a higher precision compared to recall, because we don't want to mistakenly accuse a candidate of giving an off-topic response. Also, all the results provided are ensembled results across several initialization seeds. It is quite evident from the results that both the HATM and the MSGM struggle more on the unseen compared to the seen dataset. It is also noteworthy from the position recall curves that the multi-channel SGM performs substantially better than the SGM on its own. We can already see too that the HATM has a different shape than the SGM, as the HATM has a rapid degradation in its position for high recall, while the decay is more gradual for the SGM. For those of you who aren't too familiar with position recall curves, all you really need to know is the ideal position recall curve is one which goes along the top and then vertically down the right-hand edge. That will be the ideal scenario. So we want to be as close as possible to the top right-hand corner. For the rest of the results in the presentation, I won't give you the exact position and recall values, the P and R values, and I'll just focus on the F0.5 scores themselves. Earlier, I introduced prompt dropout and data augmentation as modification strategies for the HATM. Since the model struggles with unseen prompts, these results are only on the unseen evaluation dataset. And the key we are using: B for baseline, PD for prompt dropout, AE for structured augmentation, so that's the synonym replacement and such techniques, and AM for the translation, back translation methods. We can see that the prompt dropout improves performance of the baseline system from 0.657 to 0.683. Both the augmentation strategies produce a boost in performance, but the machine translation method achieves larger gains. However, we can note that the two augmentation strategies are complementary, as the baseline is boosted to an F0.5 value of 0.782 with prompt dropout and both the augmentation strategies. This extended form of the HATM is now used to compare and combine with the MSGM model. It is immediately obvious that the precision recall curves for the extended HATM displays different characteristics to the MSGM on the unseen dataset. More interestingly, these contrasting shape curves are complementary, as combining the systems by averaging their outputs yields precision recall curves which boost the precision at each recall level. So, our best combined system achieves 0.935 on the seen dataset and 0.814 on the unseen dataset. The final part of the paper explores how well the best combined model handles specific prompts. One would expect the performance on responses from a given prompt will depend on the nature of the prompt, but also on how close the test prompt is to the set of prompts seen during training. In the figure, we can see 10 points plotted that correspond to the most common prompts in the unseen evaluation dataset. The y-axis represents the performance of the system on responses for the given prompt, and the x-axis indicates how far away the test prompt was to the closest seen prompt. This distance was calculated in the prompt embedding space that the HATM had learned during training. We see a strong negative correlation that matches the intuitive expectation that the model performs better on unseen prompts that are closer in meaning to a prompt seen during training. As an additional experiment, all the prompts in the unseen dataset were partitioned into two groups called far and close by partitioning them using a distance threshold of 0.24. The far prompts had an F0.5 or 0.777, while the close prompts achieved a greater value of 0.833. This encourages us to think of the distance of a test prompt from the closest seen prompt as a metric that can be used to predict whether an off-topic model will need to be retrained on new prompts introduced in a test. In summary, off-topic detection is a much-needed tool in any computerized spoken language assessment system. The HATM was specifically improved through regularization and augmentation, and when combined with the MSGM, it was clearly complementary in nature, achieving further gains. With some prompt-specific analysis, we can begin to determine how effective an off-topic model may be on new unseen prompts, and hence we know whether we need to retrain the system by collecting additional responses for the new prompt. thank you for the time. I hope you enjoy the presentation, and I look forward to some questions now.
Okay, let's come back. Thank you a lot, Vatsal, for the very informative presentation. I especially like the last part where you kind of like there's a type of interpretability in there that you can actually look at to see whether or not your unseen prompt is actually looking at the embedding space of the scene prompt and whether or not it's catching all the information there. Now, let me just remind folks in the audience that you can put your questions in the chat and I'll be able to get it across to Vatsal. So
Okay.
we have none so far, so I can I actually have one for you. So we understand that your paper relies on a lot of literature and research that came beforehand regarding the HATM model and the SGM model. So can you explain more clearly a little bit about the intuition behind the attention mechanism and the role it plays in the HATM model?
Yes, of course. Well, so as I implied in the presentation, the HATM consists of two attention mechanisms, the prompt attention mechanism and the response attention mechanism. Let me bring up the slide with the models. Mechanism. So here, we've got the HATM here. And you can see in the orange, I've denoted the prompt attention mechanism. And the response attention mechanism is represented in the green arrows at the bottom of the diagram. Let us have a look at the prompt attention mechanism first, as this is the more interesting one. And we found it brought substantial improvement to the ATM. So the ATM, just the attention topic model without the H. And the only difference really between the ATM and the HATM was that the ATM did not have this prompt attention mechanism. The first step in calculating a particular attention weight makes use of something we call the similarity function, which in our case is just a simple tangent function, if you know what that is. But essentially what we have to really take away is what a similarity function tells us is how similar is our key to what we are attending over. So in this specific example, our key here is this hatted HP. And we're trying to find an attention weight for each of these tilde HPs, which is the scene prompt embeddings. And the attention weight kind of represents how similar is this test prompt to any one of my scene prompts. Hence, the ith attention weight returns a level of similarity between the test prompt embedding and the ith scene prompt embedding. The softmax is simply applied to all these attention weights in order to just normalize them to make sure they add up to 1. So they actually are weights. So now once we have this understanding, the prompt attention mechanism is highly interpretable, as we can use the attention weights to deem which scene prompt is our test prompt most similar to. Then it is reasonable to represent a revised sentence level embedding of the test prompt as a weighted sum of the scene prompt embeddings, where the weights are the corresponding attention weights. So here we've got the output here, HP, is this refined prompt embedding of a test prompt. So the unrefined one was the hatted HP, then we refine it by passing it to the prompt attention mechanism to generate a refined prompt embedding. So why is this hierarchical prompt attention mechanism so effective for us? Why did it improve our performance compared to the ATM so much? Well, to offer a glimpse of intuition, the test prompt, which is now unseen, let's consider the test prompt here, essentially locks on to a set of the scene prompts that are most similar to it in the prompt embedding space. And handling the scene prompts henceforth in the model is a lot easier for the model, as the scene prompts were used to train the system in the first place. So the perceptive amongst you may point out that we make a big assumption for the setup of the prompt attention mechanism to work. The set of scene prompts must be sufficiently diverse to cover all parts of the prompt embedding space, such that the test prompt is reasonably close to at least one of the scene prompts. Well, yes, that's a valid assumption, and which is why in our data we have 379 unique prompts that hope to cover all possible parts of the prompt space. And this is hopefully improved by the augmentation strategy that I discussed during the presentation too. Now let's look at the other attention mechanism in the model, which is the response attention mechanism. This is quite a standard use of an attention mechanism. In this particular case, the refined prompt embedding that was calculated from the prompt attention mechanism is used as the key for the response attention mechanism. This response attention mechanism attends with the word embeddings of the response words. So the response attention mechanism simply acts as a means by which the prompt and response can be combined into a single vector that can then be passed onto the classifier to produce the required relevance score. I hope that makes sense. And yeah. Anything else? Any other questions? No worries.
Okay, hello guys. Sorry about that. I think I had just a little bit of an internet connection issue there. Okay, so as I read from Vatsal's paper, I think I could summarize a little bit of what he was talking about. So basically, there are two attention mechanisms being utilized. And the prompt attention helps the algorithm become more robust by representing the unseen prompt as a combination of some sort of similar scene prompt. And the response attention helps to create the prompt response embedding and look for similarities. That was super interesting, and it's interesting to me how the attention mechanism can be used in a flexible way like this, and it was really enjoyable to go deep into your paper and see how it plays out.
That's great.
So regarding the SGM model, can you elaborate more about the Inception Network being used? And I was under the impression that the Inception networks are often used in computer vision.
Yes, good question and good impression as well. So yeah, as you correctly said, the area of computer vision has demonstrated large advances using deep convolutional neural networks. And the evolution of the Inception network is largely responsible for these advances, as this Inception network is simply a network which comprises of a hand-tuned architecture with multiple size convolutional filters in parallel, while a typical CNN would be maybe convolutional filters of 3x3s by 5x5s. Inception networks manage to make this far more efficient and hence more effective when used in place of traditional CNNs. So in our specific case of the SGM, we have constructed something we call the similarity grid. It is very easy to think of this as an image where each cell position represents an intensity value. In fact, the interpretation of the similarity grid as an image is even more justified when we look at the MSGM. So if you recall, by the MSGM, we mean we have multiple channels, like we have in our case, we have 3 channels. So we use these additional channels to encode more information, as we can think of this as something analogous to the, perhaps in the computer vision world, to the RGB color channels, red, green, blue color channels in a typical image. So for all intents and purposes, our similarity grid can essentially be treated like an image, and we can use a typical computer vision methods to help classify this as one of our classes. And that's simply using some form of a convolutional neural network. And we've gone for more of the state-of-the-art ones, which is an Inception network. So we're compelled to pass the similarity grid through this Inception network to use the spatial locality of the embeddings in the image to determine our relevance score. Note, I've specifically chosen the ResNet 152, but other state-of-the-art ResNets will be equally effective as this one. I hope that helps give some insight into the similarity grid model and the Inception network too.
Yes, definitely. The idea of treating the prompt response similarity as a pixelated image is fascinating, and I've never seen that kind of architecture before. It's really interesting to me how the advances in the computer vision space has led to some development of models in NLP.
Yeah.
So one more question. Can you give us some specific examples of augmentation of training examples using machine translation? Because what I'm concerned about is whether or not the augmented data will really be able to generate as I got from your paper, 10 times the amount of training data.
Yes, that's correct. So we did augment our training data by a factor of 10 using the augmentation strategies we mentioned. So let me see if I can get the slide. So yeah, so the two augmentation strategies are the structured techniques and the unstructured techniques. I get from your question, you're more worried about the back translation process, where you use machine translation to augment our data. So as a quick reminder to those who might have missed the meaning of back translation with machine translation, back translation is where a given training prompt is translated to a foreign language using a typical translation model and then translated back into English. In both directions, we use the one best hypothesis, as we say it. So we take the best output from the translation model, and we don't care about any of the second, third, fourth best ones. So this process of translating to a foreign language and translating back from that foreign language allows us to generate two prompts that are similar in meaning, but use synonymous choice of words and may have a different structure in the overall structure altogether. Now, the original prompt and the new prompt can be paired with the original prompt's response. So by repeating this process 10 times, we can essentially augment our training data on the prompt side by up to a factor of 10, like we did in our paper. I'm not permitted to reveal real prompts from the data, as they feature in actual spoken exams. But to show you the real power of using this technique of machine translation, anyone in the audience later on, even now, can try the following in their browser or perhaps on a different screen. You just simply navigate to, let's say, Google Translate, select English to French, and in English type, let's say an example of a realistic prompt might be discuss the positives and drawbacks of your typical working day. Now, let's click the translate button and see what we generate in French. And now let's reverse the translation process by copying and pasting that French text and translating it back to English. And when you do this process, we see a sentence that has a very similar meaning, but has been differently worded. So now the original sentence, which was discuss the positives and drawbacks of a typical working day, have now been back translated to produce discuss the pros and cons of your typical workday, which in my opinion is quite remarkable. So this technique of machine translation is particularly valuable and effective for topic relevant systems compared to other NLP tasks, because the back translation process retains the meaning of the prompt sentence and the word choice, while the ordering is less important of the words themselves. Also, the new back translated sentence remains syntactically sensible because it has gone through a actual machine translation model, and these do ensure the sentences are realistic of what humans might say once they translate to a different language. I think it would be misleading to say that the training data has been expanded by a factor of 10, as no new differently meaning prompts have been included. It is perhaps more sensible to say that the back translation process helps the model to truly understand the meaning of each of the scene prompts and really concentrate on the topical meaning rather than any other aspect of the specific prompt. I hope that helps answer the question why perhaps we can trust that the augmentation strategy is working. And I guess it's not really expanding by a factor of 10, but it is helping the model to learn. I guess one other point I might mention of augmentation, a good visualization I like to have of augmentation, is imagine you have a lot of discrete points as our training data points, as the training data points. And by applying any augmentation strategy, what you can think of as is these discrete points have been smeared. So these discrete points have a bit of exploration around them, which allows them to be more effective as we're covering the prompt space more continuously rather than as individual discrete points as we had in our original training data, which is the real advantage of any augmentation strategy.
I see. That makes a lot of sense. Was there a reason you chose to augment the prompt side, but not the response side?
Well, yeah, so there are actually a couple of reasons why we focused our augmentation strategies on only the prompt side for the hierarchical attention topic model and chose not to augment the response size. So just to reiterate, you may have noticed that both our augmentation techniques of machine translation and EDA techniques will only apply to the specific prompts. But one could easily argue that why not augment the responses too? Surely that would increase the size of the training data dramatically, and the smearing of the discrete data points I talked about surely applies to the response side as well as to the prompt side. Well, I hinted at one of these reasons for why not during my presentation. As we can see on the data slide, let me see if I can find that. Here it is. There are far more responses than prompts, meaning there is a limited scope of improvement by augmenting the responses, as the model has already come across a very large variety during training. Also, a more subtle reason is that the prompts are text-based, while the responses are just transcribed to text using an ASR system, automatic speech recognition system, because the responses were actually spoken by real people, while the prompts were pre-known, so they can be input as textual inputs. And any ASR system has a word error rate. In our specific example, the error rate of the ASR system was about 25%, which means in the transcribing process, it will every like maybe 1 in 4, 1 in 5 words will be incorrectly transcribed to the wrong word, which might mean that the sentence does not flow in the same way, in textual way, as the prompt did itself. Which means it is very challenging in augmenting these, I guess, responses with errors inside them, because any augmentation strategy will not give you convincing augmented versions of the responses. And by convincing, I mean you are unlikely to come across a new test prompt which gets to that part of the prompt space, because no one would say a phrase in that manner, the way it's been transcribed and augmented. Well, I guess as a sanity check, we had tested augmenting the responses. And indeed, when we did test it and evaluate on our 2 evaluation data sets, we did find that it had no improvement compared to our baseline system. Yeah.
Yeah, that was great rationale. So I understand that this is mainly used for the testing service industry. Would there be any other applications in other industry where this can be extended to?
Well, as you have correctly said, the main purpose of designing a topic relevance system in this context is with the educational testing bodies that aim to assess the competencies of an individual taking, let's say, a spoken test. However, topic relevance systems are used and can be used in many other areas. So at the top of my head, for example, the task of document retrieval in any search engine requires the documents to be ranked from the most relevant to the least relevant. So for example, we do a Google search, Google has to rank all the documents from what it thinks will be most useful to you to least useful. By interpreting the query in the search engine as a prompt and each document as a response to the prompt, we can apply our topic relevance system to return a relevance score between the search query and the retrieved documents. Hence, the topic relevance system can act as a filter of sorts to only extract the most relevant documents or websites in the case of a search engine like Google. Another possible application of topic relevance systems could be for validating the quality of automated personal assistants such as Google Home and Amazon's Alexa. During development of such automated assistants, one of the factors to assess the response to a human question may be the level of relevance to the posed question given by the personal assistant, automated personal assistant. Hence, a topic relevance system could be directly used in such a situation. I'm sure besides testing services, document retrieval, and validation tasks, a topic relevance system could be used like in a plethora of different contexts that I'm sure even some of you may come up with.
Yeah, most definitely. In these day and age of information overload, I think relevancy is very much needed. I could imagine that in the future, I'll just be able to have an automatic BS filter for all the stuff that I'm receiving, right? Um, I also noticed that you decided to use F beta as your evaluation metric.
Yeah.
Can you give us some sort of best practices in terms of using and determining beta for your F beta score?
Okay, so let me see if I can take you to, so I've used F0.5 specifically, my beta of 0.5 in my performance metric. Well, to make sure we are all on the same page, the F beta score is some kind of weighted mean of the precision and recall values, where the beta dictates the importance of the recall or precision. So in an optimal scenario, the F beta score has a value of 1 and 0 in the worst case scenario. Now, an obvious question when selecting a performance metric is how should we select the beta value? One of the most common choices of beta is 1, as it equally weights the precision and recall values. However, in the evaluation of our models, we have decided to go for F0.5 as our performance metric, i.e. our beta value has a value of 0.5. This means we weigh precision more than recall. But why? Why should we weigh precision more than recall? My answer to that is context is everything. In our specific case, precision is preferred over recall because our task requires the identification of off-topic responses that will be assigned a score of 0, as it will be assumed the student is committing some form of malpractice or perhaps did not understand the question. And so it's quite a harsh punishment, really, to give someone a score of 0 on their response to a given question. Thus, it's like, given it's such a serious issue, if the topic relevance system misclassifies an on-topic response as off-topic by accident, perhaps, while the reverse situation is not as much of a big deal, i.e. it doesn't matter as much if our off-topic detector misses to identify maybe 1 or 2 off-topic responses here and there. which is why it's so much more important that we make sure that our off-topic system does not accuse, I guess, a candidate of making an off-topic response, which is why we favor precision over recall. So like in conclusion, I guess, when choosing your beta value, consider how balanced your task is. Is the reverse equally important as the forward scenario? Well, some of you may also ask, then why not choose a beta value of, let's say, 0.4 instead of 0.5? How did I randomly choose 0.5? Like, does that mean precision is twice as more important as recall? And why do you want that to be the case? Why can't I go for 0.3 maybe? Well, as an industry, we want a level of standardization across performance metrics. So it makes it a lot easier to compare results from different studies. Hence, something like F0.4 is probably not a great idea as a performance metric, as you won't be able to compare results in a transparent and easy manner with other similar pieces of work.
Yeah, that was very good. I mean, as an ML practitioner, I always find using F score like more intuitive and more easy to interpret than using stuff like AUC, especially
Yeah.
when you're dealing with um, people who are not necessarily in the technical field.
Yeah.
So how was the result of this result of your best ensemble on unseen prompts compared to other studies?
So prior to this paper, there have been like two main groups who have worked on the area of topic detection for the application to spoken language assessment in standardized tests. So the two main groups, if I can bring that slide up here. These are the two main groups. So I'll give an example of one of these, a paper from each of these groups. I believe there is one group that's affiliated with the ETS, so this is the bottom one here, who administer various standardized tests. And the other group is here itself, where I am in Cambridge, the speech research group in the engineering department. The ETS group was the one that developed the similarity grid model, and the research group here developed the HATM. The work in this paper essentially demonstrated that by combining enhanced versions of these two systems, two different groups, it is possible to improve performance for prompts not seen during training, as these two systems appear to be complementary in nature due to drastically different approaches utilized. However, the ETS group did not report the performance of the system on their unseen prompts, but they chose to focus their work on the seen prompts. So we can't compare our performance metrics in that sense. Also, they used F1 score as a performance metric, while we use F0.5. But in order to compare, we also reported our F1 scores of our best system on the seen and unseen data sets. So if I recall correctly, we had an F1 score of 0.807 on the unseen and 0.922 on the seen data set. So that means I think the ETS had a score about in their paper about 928 on their seen data set, which is very similar to us, though I guess it isn't entirely fair to compare directly, as we don't know too much of the kind of exact data that they have been using. And likewise, they don't know too much about our data, which makes it quite challenging to compare numbers on the absolute values.
So perhaps there's some kind of rivalry going on. Um, yeah, I guess cooperation would greatly resolve this issue, but I think the competition is also generating some pretty good performance, right?
Though I guess it's more we're not allowed to reveal our data and they're not allowed to reveal their data because it's actually used in real exams.
Oh, that makes sense.
Yeah.
Well, I have one last question for you. And so, with the recent advent in the language models like BERT and GPT, how do you imagine those will be or can be used in the future to improve your algorithm?
So quite interestingly, about last year at this time, we did try and incorporate BERT into our hierarchical attention topic model. So this is where we use BERT directly for the sentence embedding representations of the scene prompts. So if you could just get that slide quickly. Yeah, so these sentence embeddings, we decided instead of using this prompt encoder, why not use BERT directly for it? Because it's been so well trained on large amounts of data, it should have a pretty good prompt embedding representation of it. However, when we used BERT, it didn't directly, simply by replacing this prompt encoder, it did not improve performance. And we have, I guess, a justification for why that did not happen. So because BERT has been trained, their model has been trained on such a large, diverse amount of data, it can come up with very contextually dependent representations of any given sentence. But the topics we are talking about in our specific examples are a very small niche. So all the topics are all very similar, which means BERT will struggle to produce very diversely different sentence embeddings on sentences which are very similar in meaning. But then someone might say, why not fine-tune the BERT model to make it more apt for our specific case? But the issue with that is we have only 379 unique prompts, so it makes the fine-tuning not very effective when you have such little data on a model which has been trained on such a large amount of data. So in the future, in order to be able to use BERT more effectively, we need to think of a good bridging method, essentially, for how we could use BERT. Perhaps don't use it for the sentence embedding representations, but use right at the earlier stage for the word embedding representations. And that might have more of a trickle effect of a model and be able to use the amazing advances that BERT and all the GPT models have demonstrated recently.
Yeah, it goes to show that you really need to think about your architecture. So there's no general one thing could solve all your problem, right?
Exactly.
So Vatsal, it seems that our time is up for this session. I learned so much in our session, but unfortunately we have to end here. On the behalf of ACE and the audience, I would like to thank you again for the afternoon to speak with us. Do you have any final remarks for the audience?
Well, I hope you enjoyed your time listening to me babble, and hopefully I have been able to impart some of my passion of topic detection for spoken language assessment and perhaps incite you to look into this area a little more.
Mm-hmm. Well, those were some very sensible babble you got. Well, before we end, I would like to remind the audience to check out the paper and the code we provided. And please put out the word for Vatsal on social media if you find his work interesting. And that'll be all for today. Have a great day, everyone.
Great. Thank you.
Thank you.